Thank you for inviting me, and thank everyone
for a change. There are slides. Yes, there are slides. You're not writing with a pen.
Yes, I'm not writing, and this is not a paper on bandits either. So this is about
no, but that's connected to what Eran talked in the last week, right?
Yes, but this is the second half of the paper, so it's going to be different. Yeah. Okay.
Very
so
good.
you're welcome. So this is a project choice from a verifiable proposal, and this is the last talk of the day. So I'm going to begin with a very, very simple example we are all very familiar with. And this is not a perfect example, but it will help us fix ideas, right? So let's think about the situation in which a department has a hiring slot open, and the department learns that the available candidates are triangle, square, diamond, and a star. The department proposes a short list to the dean, and the dean decides if she wants to make an offer, and if yes, who to make an offer to. Okay. Now, going beyond our little word, in general, we can think about this as a project choice in organization. So a division may have a chance to choose an office building, and it learns that the available locations are given by L, M, and P. So the division is asked to propose a short list for the headquarters to evaluate and choose. Okay, so this type of project choice project choice is one of the most important functions of an organization. It typically involves two parties. So there is an agent at a lower hierarchical level. The agent has expertise and proposes projects to the principal. Okay, the principal is located at a higher hierarchical level, and she can decide, she can evaluate the proposed projects and makes the final choice. Okay. Now, in this type of situation, we want to understand how the principal should encourage the agent to propose the principal's preferred projects. On top of that, what is the principal's optimal mechanism for choosing a project? If the principal wants a mechanism that works fairly well in all the circumstances, what should this mechanism look like? Okay, so as I promised, this is the second part of the paper. So today's talk is going to focus on multi-project proposals, or what I call the short list, right? So we want to understand why people propose a short list instead of a single project, even though at most one project will be chosen in the end. Okay, so in other words, we want to understand the role played by short list proposals in this type of project choice problems. Okay. Now, if there is no question, I'm going to move to the model, and we let capital D to represent the domain or the set of all possible verifiable projects. Okay, so this capital D is a box given by this gray area. Okay, now U lower bar, so each project in this box is represented by two numbers. So the first number U is the project's payoff to the agent. The second number V is the project's payoff to the principal. Now, for the talk, we assume that the lowest payoff to the principal is 0, and the lowest payoff to the agent is given by U lower bar. Okay, so as U lower bar gets higher, it becomes easier to align the incentives between the agent and the principal. So we will show how this will affect the result. Okay. Now, if project UV is chosen, as we said before, the agent gets U dollars and the principal gets V dollars. If no project is chosen, both players will get a payoff of 0. Okay, so any questions so far? Okay, if not, let me move on to the interesting part. Okay, so now the agent has expertise, and he privately observes the set of available projects, which is denoted by capital A. Okay, so this capital A is agent's private information, and we also call it the agent's type. And the agent can propose a set P, capital P, of projects to the principal. The only requirement we make is that the agent can propose only available projects. So P is a subset of A, right? This is what we meant earlier, that the projects are verifiable. Now, this is the main departure also from Eran's talk last week, right? So last week, P has to be singleton. Now, a mechanism rho attaches to each proposal P a sub-probability measure rho P over the proposal P. So this rho UV is the probability that I would choose this project UV, and the sum of the total probability of choosing a project has to be smaller than 1. Okay, so that's what we meant by sub-probability measure, and the principal can commit to mechanism rho. Any questions so far? Okay, let me see. Now, the principal's problem is to design the mechanism to minimize his worst case regret, right? So given a mechanism rho and given the agent's type A, the agent will of course choose a proposal to maximize his own payoff. So he will choose a proposal to maximize his expected payoff from proposing P on the mechanism rho. Now the principal's regret is given by the difference between the maximum payoff he could get if he knew the agent's private information and the realized payoff he will get. Okay, now in this world, we are interested in settings where the information asymmetry is so pronounced that the principal does not have a prior belief. Instead, he chooses a mechanism rho to maximize his worst case regret. And the worst case regret is a maximum regret across all possible agents types. Okay, so this is the principal's program. Any questions so far? Okay, good. So now, before I move to the formal result, a very quick literature review. So this is closely related to the project choice literature, in particular the papers by Armstrong, Vickers, and Nog and Winston. So the main departure from these two papers is also the shortlist assumption, right? So they have a focus on single project proposal, and they have a focus on deterministic mechanism. And we are also closely related to, for the sake of this conference, I should really call this strategic communication with hard evidence. Okay, so in particular, our environment also satisfies the normality in this evidence literature. So a revelation principle holds in our environment as well. And the main departure we have from this literature is that the proposal not only provides evidence to the agent's private information, it also determines the action space of the principal. Okay, so that's our main departure from this area. So the agent has private information. The agent also has proposal setting power, as in the department versus dean situation. Okay. Lastly, the worst case regret approach is very, very popular in computer science. There is also a small and active literature within econ. So Dirk has some very nice papers on monopoly pricing, and my colleague Chuck Mansky is a big fan of this approach as well. And more broadly, we contribute to the robust mechanism design literature. And this is a very nice survey by Carol. Okay, so that's a very brief literature review. Any questions so far? Good. If not, let me move on to the main result. Okay, I'm going to begin with a very simple example, which illustrates the trade-off, the fundamental trade-off faced by the principal, and also it will illustrate the main idea of the optimal mechanism. So for this discussion, I will begin with a restriction, right? So let's first look at what happens when the principal can only use a deterministic mechanism. Okay, so in this case, the probability of choosing a particular project can be either 0 or 1 for any UV and any proposal P. Okay, so let me look at these two projects in our domain. So the first project is this triangle project. So this triangle project gives the agent his maximum payoff of 1. Okay, so this is the agent's favorite project, the best ever project for the agent. It also gives the principal a moderate payoff, 1/2. Okay. Now the second project is given by this star, and this project gives the principal his highest payoff 1, and it gives 0 to the agent, right? As you can see, the principal will really have a difficult time motivating the agent to propose star when the agent actually has the triangle in his pocket, right? So that's going to be the main struggle here. So let's do a small thought experiment, and let's ask ourselves this question: should the principal approve this triangle if the agent proposes this triangle alone, right? So now if the principal says that I will approve the triangle if you propose it, in the sense that the row triangle, given triangle, is equal to 1. Now, the real problem is that now the agent would never propose star, right? So if the agent has star and a triangle, the agent will propose triangle, and the principal would suffer a regret of 1/2. Okay. Now, let's look at the second possibility. The principal tells the agent that I'm going to be tough, right? So if you present triangle alone, I'm going to reject it. Now, in this case, it's possible that triangle is the only project available. And by rejecting this project, the principal also suffers a regret of 1/2. Right? So as you can see, this example shows that no matter what the principal does, the worst case regret under deterministic mechanisms is always at least 1/2. In fact, the principal can tell the agent that as long as you give me 1/2, I will approve your project. That mechanism is the optimal deterministic mechanism. Okay. Now let's see what the principal can do with randomization. Right, so under deterministic mechanism, whenever the agent proposes star and the triangle, the principal has to either choose triangle or star or nothing, right? If the principal can randomize, he can strike a compromise between the principal and agent by choosing each project with some probability. Okay, now let's see, this is a very, very intuitive idea, but let's see how it plays in the project choice problem. Okay, let's go back to our example. And the principal now is going to tell the agent the following. If you propose star and the triangle, we're going to split the pie. Okay, I'm going to choose each project with probability 1/2. Okay, now if you propose a triangle alone, I'm going to choose a triangle with probability 1/2, and with probability 1/2, I'm going to reject it. Okay. Now, the first observation is that this mechanism will preserve the agent's incentive to include a star whenever star is available. Right, so because basically the principal is just going to allocate the rejection probability to the star. It doesn't affect the agent's payoff, right? So that's the incentive compatibility part. On top of that, if the principal actually, if triangle is the only available project, the principal will reduce the amount of inefficient rejection. So in this case, the regret is going to be just 1/4, both when the available projects are star and the triangle, and when the available project is just the triangle. Right? So this is how the randomization helps in this environment. As you can see already, the shortlist environment will help the principal only when randomization is allowed. Right? So the kind of shortlist and the randomization goes together all the time. Now, any questions about this example so far? I only see 4 people, but I see nodding heads all the time, so I'm happy about it. Okay, good. So I'll move on to the optimal mechanism. Of course, this example is extremely simple, and as you can tell, this is a very, very difficult problem to solve. But in the end, we will show you that actually the optimal mechanism is as intuitive as the example we were just seeing. Okay. Now, the optimal mechanism First of all, I have to introduce what happens when the agent just propose a single project triangle. So if this is the proposal, the principal will tell the agent that I'm going to offer a two-tier mechanism. This is similar to last week's result. So the top tier, if your project is above a certain bar for the principal, then I'm going to approve it for sure. Okay, so you can think about this as the slam dunk project or the above bar project. Now, if your project is below this dashed line, then I'm going to say that these are the projects that are at the border, and I will approve it with a probability that depends on its attributes, right? So in particular, this probability is increasing in V in the principal's payoff and decreasing in U in the agent's payoff, right? The decreasing in U part is there just to provide incentives for the agent not to hide good project for principal. Now, this is what the agent will get if he just proposes one project. What happens, let's look at what happens if the agent actually proposes multiple projects, right? So if the agent tells me that there are 3 candidates available, triangle, square, and star. So what the principal will do is he will randomize over these 3 projects with the promise that the agent will get his maximum payoff from proposing each project alone, right? So the agent always has the option to just propose one of these 3 projects. So if your mechanism is incentive compatible, you have to promise the agent what he would get from proposing each project alone. So that's the minimal requirement for incentive compatibility. And in the optimal mechanism, actually, this is exactly promised to the agent. And this is what we call the project-wide maximum payoff for the agent, right? So he always gets the maximum payoff from proposing each project alone. And in this case, this triangle is actually the maximizer for this program. So the triangle will pin down the agent's payoff eventually from the project. Okay, formally, this is a linear programming that the principal would like to solve. And he tries to maximize his payoff subject to the idea that agent's payoff is equal to the maximum payoff from proposing each project alone. Okay. Now, the formal result is given by this theorem. So the first part is saying that the worst case regret under any mechanism is at least this capital R, and this R is defined as the max mean of the maximum of this term. And I wouldn't have time to talk about it, but if you're interested, I'm happy to continue offline. And the project-wide maximum payoff mechanism we just introduced, which is induced by this single project approval probability, has the worst case regret of this capital R. So it is an optimal mechanism for the principal. And from yesterday's talk, we know that typically there are many robustly optimal mechanisms for the principal. And the mechanism here actually is the agent's most preferred mechanism among all the optimal mechanisms. So this is our selection criteria for this mechanism. So it's robustly optimal for the principal, and it's also agent's most preferred one among all the robustly optimal mechanisms. Okay. Any questions for this formal result, Nicola?
How do you define most preferred mechanism? Do you have some kind of distribution over UV?
Oh,
or
it's a type by type.
Type by type.
It's actually, yeah, very strong. It's type by type. For every type of the agent, this mechanism gives the agent a higher weakly higher payoff than any other optimal mechanism. Yeah.
Type is a subset of D, right? Type, what's type?
Yes.
A.
A,
So you
yes.
I see.
So for every finite subset of D, this mechanism gives the agent a higher payoff than any other optimal mechanism. We also restrict attention to admissible mechanisms, which are not weakly dominated. So that's, okay, good. Now I have 3 more minutes. And so this picture actually shows the worst case regret as a function of the U lower bar, right? So U lower bar is is the kind of lowest payoff for the agent, right? Remember our capital D is given by this set. And as you know, that goes from 0 to 1, the agent's payoff from the projects are getting more and more homogeneous. So intuitively, it's going to be easier to incentivize the agent. And intuitively, the worst case regret should be smaller. And this is actually confirmed by this solid line, right? So this solid line shows that as ULOBA goes from 0 to 1, and the worst case regret goes from 1/4 to 0. And in contrast, if we just look at the deterministic mechanism, the worst case regret is going to be constant at 1/2, as we said at the beginning. Yeah. Okay, now, so I'll use the last 2 minutes just to go back, right? You have seen how the principal would incentivize the agent, and also you have seen what the optimal mechanism looks like. In the end, I want to talk about what is actually the role of a shortlist proposal versus single project proposal, right? So you don't have to be at last week's talk. So I'll try to be as intuitive as possible. So if the agent can propose at most 1 project, now that means the fallback option is to reject the proposed project, right? So the only way to punish the agent is to reject his project. And this is a very costly fallback option. This is a very costly punishment in the sense that rejection gives both players a 0 payoff. Now, right? Now, if you allow the agent to propose multiple projects or to propose a short list, that allows the agent to propose better fallback options than rejection or than rejecting the project. Now, the most efficient fallback option or the most efficient punishment is the project that gives the principal a high payoff, and that gives the agent a low payoff, right? So this is kind of the most efficient instrument that you should use in this case. In particular, if we go back to the 3 project proposal, this star is going to be more efficient a fallback option than this square. So anything that is in the northwest direction is a better fallback option than this square option. So in particular, you don't actually have to ask agent to propose 3 projects, right? So you can just ask agent to propose 2 of them. So this triangle project pins down agent's payoff is what agent prefers to see in the end. And the agent would also propose a project that is good for the principal. So if the principal does not choose the triangle, he can just choose this star, which is not perfect for the agent, but is also giving the agent something in reality. Okay, so based by this observation, we also have a result which is called 2 is enough, right? So far we basically we make the assumption that the agent can propose any subset of the set of available projects. Suppose the principal can verify up to k projects, not an infinite number of projects. And our next result says that actually 2 projects are enough, right? So for any k, any constant k which is greater than 2, the previous project-wide maximum payoff mechanism induced by the same approval probability is actually optimal in the k project environment. Okay, so the worst case regret under this mechanism is exactly the same as the infinite verification capacity environment. So this shows that actually moving from 1 to 2 is a huge step forward, but once you can propose up to 2 projects, that's enough. Okay, Nicola?
Yes, I was wondering, so in your mechanism, assume I'm the agent, and I list among my proposals something that is very bad for you and very good for me, but which is not in the set D, right?
So what do you mean?
I mean, I was thinking even for the previous case where when you were assuming everything was verifiable. So you how can I say that?
There's only about a minute or two left.
Okay, so maybe I can postpone my question to the online.
Okay. So yeah, I only have one, actually 2 lines to say. So this this proposition has 2 implications. The first one is that a capacity of only 2 projects is sufficient to unlock the power of making a compromise. On top of that, it also shows that even if the principal can verify up to 10, 20 projects, it suffices to let the agent propose up to 2. Okay, this is exact my 1 minute conclusion, and thank you very much for your attention. Okay, Nicholas, you want to continue?
So the K restriction is on the number of, on the size of the number of projects that the agent can propose?
Yes, yes.
Okay,
so
good.
I'm saying that
Okay.
suppose you can only propose projects such that the size is smaller than K. This is what we meant by K K project environment.
Okay.
So
The
last
agent
week
is-
it was P smaller than 1, right?
Okay, and the agent is still constrained to
Yes.
to propose only projects that exist.
Yes, so we add 1 more. Yes, that's the environment we're thinking.
Okay.
So you can see already from the optimal mechanism why 2 projects are enough, right? So you only need this star and the triangle. Yeah.
There's a question. Oh, good.
No. So if I may ask again,
Yeah.
I don't know this literature, but just as a way of comparison, you know, as a benchmark or something. What happens if the principal is interested just in maximizing his payoff rather than minimizing his regret? How does this change?
Yeah,
I mean, how does this change? I think that problem must be solved and well known, right?
You may maximize his minimal payoff, right? Max min, or the Bayesian
no, just
setting.
maximize his expected payoff. If the mechanism is stochastic, he just cares about his payoff, not
Yes.
about his to minimize his regret. And
Yeah,
that just
so
to
this-
compare to again, I'm not saying that that's
Yes, actually, I have a slide, and actually I skip it. So it's actually in our literature slide, right? So these are the.
I don't know the literature, so that must have been solved already. But what I want to know is the comparison. Does this so a principal who is worried about his regret is doing better than a principal who is just worried about his payoff, or worse? Here is a one-line question.
Okay, so that's so the comparison. So these are the 2 benchmark papers. So you can think about this as looking at the exact same project choice problems. So with some differences, right? So first of all, they're looking at the Bayesian setting, and secondly, they look at the deterministic mechanism, and they have a focus on single project proposal. So in Armstrong and Vickers, they show that the optimal mechanism is saying that we actually allow for all projects above a certain threshold. And this threshold U is the solution of an optimal control problem. And they characterize precisely that threshold. And in terms of multi-project environment, they have an extension also allow for that. They show that multi-project environment would also help in their environment, right? So the best example is that suppose you know that it's very likely there is going to be 3 projects. You can ask the agent to propose all of them. Otherwise, you just kill all the opportunities for everyone, right? So that would be a strict improvement over the single project environment.
Sergio, I think if I can interrupt, I think you make a wrong assumption. The corresponding problem to our problem in the Bayesian setup is not solved, and it's very difficult. We don't know what would be the optimal mechanism if you are allowed to randomize and present a shortlist. We just have this example that Yingni mentioned that shows that
So you say the solution to that problem is not known?
is not known.
It's
It
not.
seems to be very difficult. It's a high dimensional mechanism design.
Okay, but can you just, without solving it exactly, can you still make a comparison in terms of what the worst case payoff of the principal is going to be here and there? Maybe without solving, you can show that in the other problem we can do better or always worse. Just a thought.
I see.
That would be interesting.
So we can, I think
Maybe just some examples. I don't know. I would like to understand. In short, the worst case regret. I'm the last one who's going to criticize regret. Yes. So it's not my point. But I want to understand what the role of regret for the principal is that is playing here.
Okay. So we don't have the kind of comparison to the second best in the Bayesian setting, but we do have the comparison to the first best in the Bayesian setting, just to give you some sense here, right? So you can interpret the worst case regret as providing a payoff guarantee, which tracks the first best payoff, right? So if the first best payoff is X, then our mechanism will tell you that the principal's payoff, expected payoff, is at least the first best minus the worst case regret. Okay, so now in this case, when the first best is very high, our mechanism actually has a very nice performance. Right? So this is the first best payoff as the expected number of projects goes to infinity. So as number that goes to infinity, it's going to be the first best payoff will shoot to the principal's optimal payoff 1. And then in this case, our mechanism in a single project environment would offer expected payoff, which is given by this red curve. So, oh, sorry, this is the guarantee we offer. And this is the actual performance of our mechanism, which is pretty close to, as you can see, to the first best. Yeah, so I think the basic idea is that whenever there is going to be a high expected surplus on the table, the worst case regret approach is going to offer a very decent guarantee, and also on top of that, an even better expected payoff than the guarantee. So this is kind of the idea. It's not, so I think what you are having in mind is that maybe we can try to draw the second best payoff under the optimal mechanism. So that's going to be strictly below this black dashed line, right? So, but we don't know the solution to that question. But this picture, the blue dots is the guarantee, and the red one is the actual performance of our mechanism.